Okay, let's continue our morning section. It's a great pleasure for me to introduce His Beauty, Ustinovskii, from Leigh University. And today you talk about the generalized Kähler constant scalar curvature problem.
Yeah, thank you very much. Thank you for inviting me here, giving me the opportunity to talk here. It's my first time at the University of Miami. It's a pleasure to be here. So I'm going to talk about our recent joint work with V.Apostolov and J.Streets. And I'll start with something more classical, really. So we'll get to generalized geometry, but let's start with what's happening in Calabi geometry. Let me start with Calabi. So we have a compact manifold M, and this manifold will have a complex structure, which will be known by J, interval, and I have a symplectic form reaching this particle called omega, and they're compatible in the usual Kähler sense, which basically means omega is symplectic, the omega is closed, and omega is positive. And whenever people say omega is positive, what it really means is that when you hook J into omega, depending on conventions, you might want to put negative sign here. So this is actually a Riemannian method. Let's get that in. So that is my setup. And what the problem which people studied in Kähler geometry for a long time goes back to Gene and Calabi. We saw one of the versions of Calabi Problem yesterday in Carolina's talk. So the Calabi Problem which I'm right now is slightly more general. So you can find some slightly more general setting. You don't have to be in one of these three classes of Calabi general type or final. Actually, this is more general. So what they're looking for in this Calabi Problem, you are fixing the homology class. I fix J for now, and I also fix the homology class. So maybe I'll put zeros here, because some of these objects will change. So I also fix the homology class of omega 0. And what I want to do in this homology class, I would like to find a Kähler metric with a particularly nice properties. And it depends on what you're looking for. So yesterday we saw you might be looking for Einstein problem. For this Kähler class has to be special. But in principle, you can start with any Kähler class. And with any Kähler class, you might want to find, for instance, metric of constant scalar curvature. So Kähler class will be noted by K of omega 0. So these are all Kähler metrics which belong to the same homology class. But that's a stupid description, because in Kähler case you can say it started much better by D.D. Barlow. So you can just interpret all these metrics as omega 0 plus del bar of the smooth function. So and again, you have conditions that this is positive in the same sense as these would inform right omega possible. So this is Kähler class, and in Kähler class you might want to find a nice representative. And Calabi's problem is to find constant scalar curvature measure, and constant scalar in the usual Riemannian sense. So I will write it abbreviated as cscGK. So that's how it's usually abbreviated. Constant scalar curvature Kähler method in this class. It turns out to be extremely complex, extremely rich problem, which as a part of it contains the sort of Calabi-Einstein metrics we saw last time. And it leads to many consequences, again, as in Calabi case or Futaki case, to many implications for algebraic geometry of underlying manifold. So you kind of can think of it as a Kähler manifold, then you polarize it, for instance, for example, line bundle in it, and for this line bundle, you're trying to find some particularly nice metric. An existent or non-existent metric has a lot of many implications in algebraic geometry. Again, maybe for people more inclined to graduate geometry analysis, I might say it. So specifically, we're looking for, so you freedom here is a smooth function, and you want to prescribe the scalar which is another smooth function. The map from one smooth function to another smooth function analytically is a partial differential equation, elliptic of 4 quarters. So these are kind of difficult to do. So there is no reason for this partial differential equation to come into the solution. So that was a classical approach, right? So coming essentially from complex geometry. So there is another approach, more recent, which was initially observed by Futaki and kind of more expanded by Simon Donaldson. So let me describe this Futaki, Donaldson. So what they did actually is something very unexpected. They changed point of view. Instead of fixing J and changing the Kähler form, they did the opposite way. So now we start with the Kähler manifold still. But this time we will fix our symplectic form, not just homology class. And what we're going to do, we're going to study the space of compatible complex structures with it. And to set up in a nicer geometric way, it actually makes sense to consider not restrict on the integrable structures, also allowing some non-integral structures. It's actually kind of important to the point. So basically, you can introduce a space that we'll call AC for almost complex. That's the space of all almost complex structures J, compatible with omega naught. And by compatible, I mean just like the usual linear algebraic condition, and also using a positive definite metric. So you have the space; it's infinite dimensional for manifold. If you want this language, if you remember this language, it's not important for us at all. And on this manifold, you have an actual group active. You have a group of hamiltonian diffeomorphisms. So these are diffeomorphisms generated by Hamiltonian vector fields, which I recall are just omega naught inverse of a smooth function of Hamiltonian potential. So diffeomorphisms generated by these infinitesimal variations, and this group actually acts on this space. So if I act by Hamiltonian diffeomorphism, my omega naught is 6, Hamiltonian diffeomorphisms preserves the vector form, and J0 will. Right, so nothing interesting happens yet. So it's hard actually to imagine. When I saw it first, it was hard to imagine that there is some geometry which can be used from here. But it's kind of amazing they do it. So and kind of a fact that where geometry comes into play, that this space AC of omega 0 has a formal, I mean, we should say recast Kähler structure. Maybe to expand a little bit on this, so let me first write what is the tangent space for this. Right, so if I fix a point J in this space, we would like to consider tangent space. So this will be basically what I'm doing. I'm taking this almost complex structure and I'm taking an infinitesimal variation of this. So if my infinitesimal variation is J dot, then J dot will anti-commute with J. Just variation of this identity, and then there is also a variation compatibility condition. We'll just see that omega 0 J dot plus J dot omega 0 equals 0. So the space of all anamorphisms J dot is find this identity. And it's clear kind of that if J dot belongs to this space, then you can left multiply by J, it also will belong to this space. So this left multiplication by J is this part of this formal Kähler structure. So this is formal complex structure, which happens to be formal in group. And there's also a formal Kähler structure. Maybe I didn't notice by this big omega. So I can write a formula. So I need to explain how to relate this complex symplectic form on two tangent vectors, and the formula, which was derived, I think, by Futaki already. Again, up to constant, it's just a convention. It's a trace of J1 dot, J2 dot, and you integrate it along over your volume form. Maybe I should say that here J dot is an andomorphism of the tangent model. So all these traces make sense. All right. So it's a formal Kähler structure, some infinite dimensional manifold for manifold. It's not quite clear why it's useful yet. But existence of this hamiltonian group vector here is actually where geometry comes into play. So Leigh algebra of these hamiltonians, which I will denote by this term, it's just a space of smooth functions, right? Because these smooth functions generate hamiltonians. Well, on technically speaking, it's smooth functions modulo constants because constants generate zero vector fields. So you can normalize all your functions to have a zero mean, and I put zero here to highlight that. So this pretty momentum constant is not here. So you have a group with this Leigh algebra acting on this space on the Kähler manifold, and it happens. And it's kind of a very fruitful idea in many circumstances. You want to study interaction of this atom. So this atom happens to preserve this structure. Not on atomic reserves, it's actually, that means a moment map. And having a moment map is something very useful in this circumstances. So that's exactly the theme of balance one. Here, this action on this infinite dimensional Kähler manifold. It makes a moment map. Let me unravel what it really means. So this moment map, it will be mapped from your manifold to the dual of the Leigh algebra of the group. So that's how moment maps work. So our Leigh algebra is this one space of functions. It will be dual of the space of functions. Infinity is 0. Real values functions, and I take dual of that. So how this works? Let me write it for you. So this moment map, I will call mu the moment. So at point J, so J is a point in this space. So it will take place in the dual of the function. So it should be able to evaluate it on the function. What if I want to evaluate this on a function? What will I get?
Your considerations are the same in R. In the space of functions, or just how
here just see infinity here. There is I don't have, I mean, you probably can consider some Looper regularity.
you just throw the algebra.
Yeah, it's kind of, it's pretty formal. If you look at the derivation here, there is no regularity analysis with one. We don't need any seminars, just the right formula. So by definition, I need to give you a number, right? What this number will be. So it turns out that this number is integral of p multiplied by scalar curvature omega 0 to the n of right factorial. Where scalar is not quite usual scalar curvature. So let me say the words. So this scalar is called Hermitian scalar curvature, or maybe almost Hermitian, almost Hermitian scalar curvature. But the point is that if your structure is integrable, you can consider it an integrable point, and it kind of makes sense in the context of Calabi Problem, where we start with convex manifold. So if J is integrable, it's integrable, so it's an almost complex structure. Then this scalar curvature is the usual Riemannian scalar curvature associated with Riemann, so the classical Riemannian scalar curvature. So you clearly see some interplay with these Calabi problems. So from this setup, you immediately get constant scalar curvature. So prescribing constant scalar curvature is prescribing this line mountain constant. Yes?
Are you assuming the n compact or not?
Yes, that was compact. Yeah, thank you for this clarification. It's important that we're here from compact or integrals to exist. So one comment, if scalar curvature is constant here, and since you remember phi has zero average, this result is actually zero. So cscGK problem, which we started with, is actually equivalent J omega cscGK is equivalent to the fact that mu J is identically zero. With your moment. So this is kind of the first indication that there is something actually for this problem. But so far it's not quite direct. So let me make it more direct. I think I have to erase it. Or actually maybe I can get it here. Back to Calabi problem. How this automorphism action is actually on this space on atomic structures is related to this Kähler mass. It turns out that there is a very nice geometric relation. So let me try to do a picture of it. So let's assume that this is my Kähler mass. Kähler mass. If I look at draw it like a cone because it is a little bit like a cone, right? Because you have a specific it's a convex thing. Well, as new, I have some path here. So I start with omega naught, and I consider a path omega t. Maybe it's a path. Maybe I'm trying to solve it by some flow or something, or some variation procedure. So I get a path with this Kähler mass. So how is it related to this Kähler? It turns out that the very nice relation before the flows. So what you can do so-called Mozart tree. Whenever you have a family of symplectic forms which are homologous to each other, you can apply diffeomorphism and pull them back so that the symplectic form doesn't move at all. So Mozart tree, so you get some family of diffeomorphisms. You can call this capital PT, such that if you pull back omega t, you just get omega 0. These are diffeomorphisms. So what you get from here, you can pull back the complex structure as well, and your omega is fixed. So you immediately see we have went from this picture when complex structure is fixed to this picture where omega naught is fixed and complex structure is moving. Well, how is it moving and how is it related to the hamiltonian group? Well, there is a very simple answer to this. So we'll try to draw again formula. So imagine that this is maybe my J naught, and what I do is a Hamiltonian orbit of this J naught. Hamiltonian, my symplectic form acting on J naught. So it's orbit in this space. All inside of this space. Then it turns out that this red path which I do will be a path that transversal here. And moreover, it's not only transversal, it will be given by this formal complex structure. So in the matter of fact, it's an orbit of J times Hamiltonian of omega naught. Right? J0 thing. Maybe I should put it over here. Anyway. Oh, sorry. Yeah, sorry. It's Hamiltonian J0, but not Hamiltonian multiplied by this complex structure that should take it by J, but J will be moving along this path.
So that is sort of complexified.
Yes, exactly. It's complexified Hamiltonian group. Admittedly, it doesn't exist, so there is no notion of complexified Hamiltonian group. But morally, that's how we should think of it. So morally, we should think of it as paths fitting in complexified Hamiltonian acting on J naught. So that's what really happens here. And that's actually maybe partially answering some questions Dr. Carolina's talk yesterday about stability. So actually, the stability conditions, they were discovered in this picture, because you already see what you really want. You want to hook up zero in this Hamiltonian orbit. So you want to find zero moment in this Hamiltonian orbit. And to understand whether it exists or not, you kind of want to also know how it behaves at infinity, whether it kind of this mu increases or can it drag on and kind of converge to zero infinity. And that's clearly something about the generations of complex structure. So a complex structure degenerates possibly as we move in this orbit to infinity, if you want to comment on it. Yes, please.
Wouldn't the Hamiltonian group preserve the zero fiber?
It will, yeah. So it's all invariant and the beautiful components. So that's a very good point. So, and that's the reason why, again, morally, maybe I shouldn't write equality, but morally, you should think of Kähler class as complexified Hamiltonian modular usual Hamiltonian. So the kind of like the quotient space. And again, that's not just kind of stupid observation. It has some implications about some of the geometry of the space. Maybe I will try to highlight in the second part. Thank you for the questions. Any more questions? All right, so let's move on. And I mean, Calabi Problem has been around for I don't know, more than 50 years. Yes.
Are you guaranteed to keep zero?
No, I mean there are examples when you don't. And actually, that's the reason why Calabi Problem is actually standard. I don't want to cover it. So we do this in our paper, but it's an extra layer which is ultimately not necessary for understanding it. So there is also an extremal matrix. Extremal matrix is a relaxation of Poisson scalar projects, and you kind of have to include those. So there are examples of manifolds which do not admit Poisson scalar curvature matrix, but we can meet extremal matrix. In the sense, you sometimes don't do zero. All right. So maybe just a couple of words to say here, which usually makes sense. So what this is, what I just drew here is called GIC, geometric invariant theory interpretation of Calabi Problem. GIT problem is something about you take quotient by algebraic group, but sometimes you can take kind of its real part. Or if you want to try to find something, find something on the complex orbit, and you use the fact that there is also real orbits inside. So that's basically what's happening here. Although admittedly in multi-dimensional settings, so it's merely just used as a inspiration for what to consider, not as a real way to prove. All right, so now I think it's time to go to generalized Kähler. So to motivate it a little bit, let me suggest a couple specific questions which we'll get closer by to continue this stuff. So question one, which people in complex geometry are studying for all the time essentially. So people who want to do complex geometry don't want to do Kähler geometry. So they ask, well, can we somehow relax Kähler condition? Relax Kähler condition. So we still want some matrix, so we still want some permission background, but maybe we don't want to have the omega being zero on the being closed. And I mean, you can apply it in many ways. I do will be talking about it in the first talk later today. So one specific thing which you can do, and which we'll be doing today, is tamed condition. I will explain what it means. Tamed. When your complex structure is not compatible with a symplectic form, but it is tamed by symplectic form. That's what we're going to do. Well, it turns out that our setup actually also answers a different question. And it is, I think it's a good point why we should consider it. Because question one kind of brings us away from algebraic geometry. Person the algebraic geometry stated, well, they lose interest. So why we will lose all the nice language of algebraic geometry. So how can we be studying anything here? Question two, and this setup actually shows you that there is a lot to be done from the point of view of algebraic geometry as well. So because somehow a setting you think about described allows you to introduce naturally in all this picture holomorphic Poisson geometry. So you start with your manifold J, and you add a piece of holomorphic data instead of just considering common manifold as before. You add a holomorphic Poisson tensor, which will denote I sub J. So I sub J is a section of is a bivector of type 2, 0, complex one. So such that del bar is 0, and well, this somehow not going to spell out, but B plus 1 means its column bracket vanishes. It's like literal equals itself. So literal root of 2 bivector is 2 vector is 3 vectors, so this 2 vector is required to be 0. I mean, from the point of view of quantization and like quantitative geometry, considering Poisson brackets is very natural. People are interested in algebraic geometry about the structure of Poisson, possible Poisson tensors of different varieties. So can you somehow introduce and maybe adapt Calabi problem and all this discussion to this setup? So my point is that in this Generalized Kähler, he asked you. So any questions? It was kind of a little pitch for why you should consider this geometry. So now let me give you a specific definition. So let me first explain what this change condition is here. Symplectic form. So in symplectic form, this time we'll be calling it F. So kind of distinguish it from omega. So F is a symplectic form, and I will say that it contains complex structure J, or almost complex structure, since this condition is pointwise. If the following happens, if F of x Jx is positive for all non-zero vectors x. So once you introduce this condition obtained, you immediately acquire a method. If you consider one part of F, or if you like, if you consider symmetric part, I guess of this guy. If you consider symmetric part of this guy, it will be a Riemann method. So and this whole thing will be compatible with J, so this whole thing will be permission setting. But there is more to it. So adding symplectic form, there is more to it, and maybe I'll just make a remark. So in this case, if I consider the corresponding one part of that, this one will be very close. We heard about it from yesterday, we'll hear more today. So I'll just mention that it is very close when you by taking the del bar of this 1 form, and we'll get 0. It's just a formal consequence of F being closed. F is symplectic. This implies F1 being very close. Well, once we do this, we immediately get sort of bifurcation geometry. And why we get bifurcation geometry? Because having F and having J and F not necessarily being compatible. So F is not of type 1,1. You can hook up another complex structure, or almost complex structure for now. So you can hook up I by taking J and conjugating it with F. So more formally, it will be again to match some signs convention F inverse J star F. So if you want to act by a vector, you first act by F, you get a 1 form, then you get by J with this 1 form, and then you turn this 1 form back into a vector. This will be an almost complex structure. That vector size squared is 0. So, and the condition which is important in generalized Kähler, so that's what actually makes it the generalized Kähler structure. But we require this I being integrable. So it's an extra condition. It's not true a priori. So if you just start with F and J, such I usually will not be required to be. Definition. If I is integrable, then we will say that this pair F and J is generalized Kähler. To relate to yesterday's talk, so we already see this bidimensional description here. So we have a metric G, we have two complex structures compatible with it, I and J. And we also have a two formula. Remember, we have B. So this B will be basically coming from skew part of J. So I will not write it now because it's not super important, but it is here. Okay. Question. And this is, calculating of symplectic time. We heard about several descriptions of geometry. So one of them involves just complex structure, a pair of individual complex structures. So one of the most complex structures here will be symplectic given by this app. That's important. Well, now it was observed by Kitchen that in this case, whenever you do Kähler geometry like this, you get holomorphic Poisson tensor. And this observation of Kitchen is based on the observation made by V.Apostolov and J.Streets of their paper. They found this in the case of real coordinates. In general, and the claim is that you can plot pi. Again, there is some sign and constant conventions that can look at coordinate ball for us. It's basically commutate the 1 and J and use a method to determine the two vector. So this is the real part of a holomorphic Poisson tensor. Whenever I write something like this, you should ask me holomorphic which structure. We have two complex structures, I and J, so holomorphic which structure, which one of them. So the answer is it doesn't matter. It's holomorphic both of them. It will be you can make it from type to 0 tensor for J, and it will be J holomorphic, or you can cook type to 0 tensor for I, it also will be I holomorphic. And actually, converse it also true. So this was an observation of ball theory that, well, maybe actually I'll get to observation of ball theory in a second. Maybe let us try what algebraic identity is satisfied by all the tensors. I had a lot of tensors. I had F, J, I, and now Poisson tensor. So it turns out that in this setup, F is a series of solves. And there is no integrability involved in what I'm going to write. J plus J star F equals F I F. So this is actually the critical equation for us, and it's a critical for the entire theory. So let's think for a second what this equation tells us. I'll mention the result of all theory. So we can think about this way. You start with holomorphic Poisson manifold. You start with J and I J, and you take the part of this holomorphic Poisson tensor. And then you take F solving this equation. So this equation is kind of deformation of the usual Kähler condition. You see when pi is 0, then there is no Poisson tensor when this right hand side is 0. All it says is just that F is compatible with J in the usual Kähler setup. But once you return only Poisson tensor and you get this extra quantization term, it gets this equation gets not linear. It's not linear in F anymore, and it somehow describes generalized Kähler geometry. So the fact that it describes generalized Kähler geometry is this equation that Gauss here. So Gauss can observe is the following: if you start with holomorphic Poisson J and pi, you find a closed form satisfying this identity, then I will be automatically integrable. So if for fixed j and pi, f solves this equation, star, then I is integrable. So that's kind of the correct setup. So my point is, if you want to study some sort of analog of Kähler geometry on the Poisson manifold, you really want to study this equation. This equation, it was clearly spelled out and explained by Gualtieri, but actually it appeared way back, I think in 2004, in the paper of Ustinovskii, so from some physics considerations, so we found this equation first. All right. So this brings us to the following. So the definition of generalized Kähler class. So we had the definition of Kähler class before. We want to put it all in generalized Kähler class context. So GK class, again, maybe it depends on the fixed cohomology class. We put up 0 here. This says set of all symplectic forms of this cohomology class, solving star. It's again, it depends, I guess, as we put here also on J and pi. So that you fix the holomorphic data, you fix the cohomology data, and you get your generalized Kähler class as before. But there is a problem with this definition. It's very kind of significant, and that which makes analysis and manufacturing of this feel difficult. That it doesn't have such a nice structure as the usual Kähler class. So the usual Kähler class is sort of a convex space in a linear space. Convex subset in a linear space. This is not linear. This equation is not linear with that. It's quadratic. You can't really work with it the usual way. But what is still true, and that's kind of highlighting the fact that the relational approach is helpful here, superposition. So if you have a path ft in this generalized Kähler class, so a path, then it is always driven. So ft dot, the infinitesimal variation is always will be d dci of a function t. So just like in Kähler case, if you deform Kähler form in the Kähler class, you really deform it by ddc of a function. Here the same is true. The problem is what makes it nonlinear. That this complex structure I itself depends on that. So this whole decision is nonlinear. If J is fixed and f is changing, I also will be changing. So I should put my t there. And this actually, it was, I guess, Marco Gualtieri only understood before, but and we proved it, and we derived it from analog of T.D. Barlam and Kähler. This is one of the things which Marco did, and then Gil Calvert explained also in his lecture notes. So this existence of Hodge theory and T.D. Barlam and generalized Kähler geometry is crucial. All right, so well, we described the classes, but what would be a scalar curvature? What we want to make constant? And that was actually unclear for a long time. So there is no Riemannian connection or anything that preserves all the data. There is too much data to preserve. There is no connection that actually preserves all of it, like Mabuchi and Kähler. So what can you do? And that's the answer is kind of already here. You need to develop on the math approach to find a proper notion of scalar curvature. So I'm running short on time a little bit. Maybe I'll just formulate them as a fact. So there is a moment map picture. Map picture in this setting. Just like the Kähler ones. And this one is was developed by So first a very restricted and concrete case by Boulanger. And then after that by Goto. And I basically I'll just say one word. So what is the analog of what was before AC autonomous? Before we had AC, almost all the structures compatible with human symplectic form. Now it will be actually bigger and something much simpler. So we'll call it, I don't know, maybe I'll call it AGK because overall we get almost generalized Kähler structure. So this will be, oops, sorry, it's meant to be F. It will be all complex structures J obtained by F. It's a very natural space. It's arguably even more natural than the color case. And it's kind of a magical fact that we have a map picture here. So on this page, you still have an autonomous. And this gives you out what should be a natural notion of scalar correlation. We call it generalized Kähler correlation. So what the generalized Kähler correlation is? In non-integral case, there is no nice formula. I mean, it's something. It's like almost everything Kähler correlation. But if you are integrable, if you are honest generalized Kähler, if J and I are both happen to be integrable, then this has a nice formula which people from physics knew way before. So kind of we're quite pleased to derive the formula. So we derived it from our paper. So there will be a main term, scalar curvature of the underlying metric, and then there will be a bunch of correction terms. So one correction term is pretty common in all this things. So there is kind of, I'm not asking about constants. Constants are important here, but it's not my point here. So it's df11. So you take one part of f and you take its derivative and you measure it with respect to the metric. So it's like a coercion. And then there will be so I want to write this formula again, not because it's important to me or I don't remember, but again, if you print it out, you see the formula like this, you will know that it's kind of function. So, and here I'm just explaining what psi is. Psi is a function, and it's a very simple function. So this function, yeah, I hope I find the signs. It's basically the ratio of two volume forms. So the feature of this geometry is that somehow you have two natural volume forms which don't necessarily match. So one is a Riemannian volume form, and another volume form is a symplectic one. So yeah, and of course they match in the Kähler case, but in the Kähler case you don't have it. They are different. And in the physics literature, this function has the fancy name of dilaton. Some physical language don't ask about, I don't really understand that. That's that one. In fact, as a comment, if you're on the Calabi ground, if everything is Kähler, then F11 is the same as F, and it will be close. And these two volume forms, they match each other. So psi is constant, and this term is also valid. You recover the usual scalar curvature. Well, now what's the point of doing this? Okay, now we can formulate the Calabi Problem when we do this. And it turns out that having this scalar curvature coming from the volume allows you to recover all the classical results about usual Calabi Problem, which I didn't really formulate it to save some time. I will kind of formulate it now in generalized language. So generalized Kähler Calabi Problem.
So just to ask,
yeah,
how can you interpret this scalar curvature equation when the sign vanishes identically? Like, do you have
when you just have scalar minus 112? Well, in this setup, it doesn't happen often. I think it almost never happens with something sign 0. So we see the precise constant. So you actually have it as with sign constant. So somehow it's very natural. But there is a modification of this whole setup where you allow for different volume forms. And then you kind of can actually put any function here. And that's actually how it's usually used in physics. In physics, usually the automorphism is not fixed. You can kind of change it to your needs. All right, so generalized Kähler Calabi problem, well, it's analogous. So you want to find F in this generalized Kähler class. Again, which is prescribed by cohomology data and your holomorphic data, such that generalized Kähler curvature is constant. Identical constant. Well, and it turns out that we can say a lot about this problem. And it was kind of surprising to us because usually if you move away from Kähler geometry, you can't really say much. But here you can say all the classical stuff which is known in the Calabi Problem. So let me go on and describe. So maybe first I will introduce. I'll make an assumption that we actually can drop it, but for simplicity, I assume for now you don't need it really. But to save some words as the debate 1 and 0. There is no first one of cohomology. It's ultimately unnecessary. So in this case, we can introduce automorphism of the holomorphic data. So usually with the usual scalar curvature problem, you study automorphisms of your underlying complex manifold. So here you will be studying automorphisms of your complex manifold, which preserve your Poisson term for pi and pi G as manifolds. So this is a complex Lie group. It has a Lie algebra. Maybe I call it Lie algebra small automorphism of J1. It's Lie algebra. Consisting of holomorphic vector fields. It has an actual complex structure. And so what we can prove, so theorem 1 maybe is an analog of so-called Matsushima theorem. Matsushima, Calabi-Matsushima-Lichnerowicz, and there are many versions of it in different contexts. I'll just call it Matsushima theorem. So which says the following: if your generalized Kähler class, I'll draw this decorator so it's clear that the data is fixed. So if it admits the constant scalar curvature, it means I'll write the cscGK for generalized constant scalar curvature, generalized Kähler structure. So if it admits generalized scalar curvature constant structure, then automorphism group has to be reductive. Is reductive. So it's a complex group, so what it really says that it's a complexification of a compact real Lie group. And that's immediately gives you obstructions. So you can use this theorem and immediately deduce that in many cases you know that there are no constant scalar curvature problems. So this basically answering some of the questions about the usual Kähler cases, monoscalar case. So maybe I'll give one example which is new in this language in the sense that it wasn't present in the Kähler case before. So as my manifold, I choose projective space, projective plane. Okay. And as my Poisson structure, if I choose a zero Poisson structure, that's a classical Calabi problem. We have to be study metric, which has constant scalar curvature. What if I choose non-trivial Poisson tensor? So what is Poisson tensor really? So Poisson tensor by J, in this case at least, is a section of the anti-canonical bundle. Basically, what we are choosing is an anti-canonical divisor on P2 plus some extra related to the section and divisor. And this automorphism really depends on the divisor. And the specific divisor which you might choose, for instance, is, well, you can choose 3, 4, 1. Basically, Z cube equals 0. The Poisson tensor with the divisor. And if you choose this, you can easily figure out, I will not do the computation right now, but that this automorphism group is not reductive. So we don't have generalized Kähler constant scalar curvature here anymore, while on P2 you do that. That's a new phenomenon for sure. And if you had nice automorphism group before, but by introducing Poisson tensor, you spoiled it. But the question, which is very interesting, which we don't know how to answer, is whether you can go in the other direction. You start with something where classical Kähler quantum scale probability doesn't exist. It's abstracted by an Mabuchi period. But then you turn on some Poisson tensor, you make the automorphism look smaller and nicer, and you maybe in this case, you will be able to construct quantum scale probability. Unfortunately, we don't have examples like this. That would be really nice. Anyway, this is the first theorem. So next analogous is invariant. Again, everyone's studying this is coming from diagnosis, so we know Futaki invariant. Futaki invariant is something which obstructs the existence of Kähler Einstein and Poisson scalar probability functions. So we have an analog of this as well. Let's make a definition. Futaki invariant. So I will choose vector field in this reality. And I think of it as a real vector. Yes, please.
My question is about the so if you replace the 2 for some Grassmannian, can you do the same thing? Or?
Well, if you can calculate on a visible group and then prove that it's not reductive, yeah, it doesn't matter if it's P2 or something else.
What's the difference? What we need to compute the automorphism group?
Well, because we know what conditional group of P2, and it's just PGL2, and you basically find which subgroup which preserves its line. Okay, that's why it's so easy. All right, so Futaki invariant. So so some fact again, which follows from Generalized Kähler DD bar lemma, that such vector field will be, you can decompose it as Hamiltonian vector field plus J Hamiltonian vector field. So this is something very special to the Generalized Kähler geometry. You can't expect anything like this in general. And here I'm using this as something that you make 1 otherwise you need to reduce automorphisms. Well, and then in this case I can define Futaki invariant. So Futaki invariant of this vector it will be a number. So this number I define it as integral of this function psi against generalized Kähler curvature to the n. Well, that's fine. It's a definition, but there is a problem with this definition. The problem with this definition is that this expression on the right hand side manifestly depends on f. Yes. They're different defining signs. One of the different functions, possibly different, usually different. Defining psi are real smooth functions.
And psi is not the same psi as the scalar.
Right, it was my cat. Yeah, this is different. Good one.
One of the integral is capital 2.
No, this is small. Right. So the point is that this is the theorem which really makes it an abstract theorem. This expression does not depend on f in its generalized Kähler class. That's like just what I usually plug in. So you can choose any f to calculate. Well, I'm slightly lying here, and that's actually the core of some problems that you have with this theory. We don't know this generalized Kähler class is connected. Remember, it's defined abstractly the set of solutions and equations. So we expect it to be connected, but we don't know. So to be correct, I should put 0 here, so it's a connected component. But anyway, it gives you an abstraction for existence of the connected component, right? Because what we see, oh, actually, it's 0 here, of course. So what we see immediately that if f is cscGK, then Futaki invariant is just identical to 0 for any x in the automorphism algebra of J and phi.
White doesn't depend on phi. The invariant.
I mean, it's the definition. We decide how to define it, right? So it's our choice. But yeah, basically, it comes from the fact that this part kind of would be resolving all the structures and more of them. I mean, somehow you can put one in the one. But you can also consider vector field JX, and JX will pick up T in this case. So you'll have an analogous expression with T here for vector field JX. I got completely discard. It's fine. So it's secretly here because X here is any vector field. So this invariant works for a vector field. Anyway, so you have constant scale curvature. It's this Futaki invariant matrices. So if I can calculate this for some F0 and I get non-zero number, then this gives me an obstruction. For cscGK metric in the scalar class. Well, it's kind of component again. All right. So you see, you're recovering the classical obstructions which you expected. So I don't have much time. Let me mention one thing at least I want to mention. So again, something what we're doing so far, we're exploring things which are now very known. So this result in geometry, like invariants, again, they're from 80s. Yeah, maybe if you want some extension to extremal metrics, so we can do extremal metrics as well. Would be a little bit late, but still, we do this as a classical. So another classical thing we could do is the Mabuchi metric. Mabuchi metric on the Generalized Kähler class. So the tangent space, the tangent of this space, if you remember, variation of F here is given by dd bar dd scale function. The tangent space is given by the space of functions when you constant. So again, I have numbers for just normalize and makes them zero average. So you can define formal reincarnate metric in this space, and that's what Mabuchi in the Kähler case. We can do it in our case as well. Formula is actually the same. Maybe I call it by this bold G. So tangent space identified as functions. So maybe this will be phi and psi, and this will be just output product between those. Phi psi integrated against f to the n, to make conventions nicer. So this is just the usual output product. So it's a space with output product. Again, the manifold, but you still can work with it. You can calculate the Mabuchi connection. You can calculate the Riemannian curvature tensor on this. So what happens that the corresponding formal Riemannian curvature tensor is the section curvature is negative. If you want to calculate it on phi psi, what you get? It all check that. Okay, I think I remember. So what you get is integral of f inverse d phi psi squared. So which is non-positive. So you have negative approximation. Again, going back to the intuition you have started, it's not unexpected. It's actually very much expected because morally or intuitively, so this Generalized Kähler class in which we introduce this metric. Again, in quotes, it's the orbit of the Hamiltonian group complexified by the real Hamiltonian group. So it is like symmetric domain. And symmetric domain, some fractional domains, they are negatively first. So this is true in this case, again, albeit in the dimensions, and this identification is just formal, but this situation works here very well.
You're saying more or less like this is like a non-compact symmetric.
Exactly, like not compact, like upper half plane. Yes, like or equidistance. I'll borrow 1 minute from you, and I want to formulate one conditional uniqueness result. So we have obstructions, right? We know when results, when the metrics do not exist, Matsushima theorem, Futaki theorem. We have some conditional uniqueness. The uniqueness says the following. So if F1 and F2 in the class are constant scalar curvature, generalized Kähler. Well, you can't expect them to be the same because you often have automorphisms effect. So at the very least, you can have automorphism on projective space, for instance, like many can be pseudometrics because you can have UGL too. So if there is cscGK and there exists geodesic for this metric T between them, so T between 2 and 1. So if you can connect them by geodesic, then this geodesic actually has to be induced by a vector field from the automorphism. Then T is exponent of some vector field. And I'm now regretting that she chose 1 and 2. That means she choose 0 and 1 here. This 0 for vector field in the automorphism algebra. So basically what it's saying that there is a 1 parameter family of automorphisms of your underlying holomorphic data, which brings F0 to F1. So from this point of view, they are the same, they're not different. So that's conditional union. So it looks nice and strong, but actually it is known to be weak even in the Kähler case, because even in the Kähler case, it is quite well known that smooth geodesics they might not exist. So this is kind of where analytically it gets difficult. So you either have to use different methods, or if you want to work with geodesics, you have to allow yourself weak geodesics of not regularity C infinity, but of weak regularity, and that's your analysis is harder. So that will be very interesting to project to move on with. So one last thing about existence, result of abstractions, uniqueness existence. We have a lot of existence results on toric manifolds. So on toric manifolds with toric Poisson tensor, we have very nice existence results. I mean, they're not complete, and they kind of first suggested for kind of abundance of metrics of constant scale curvature and extremal metrics as well, and we must fail to have. So I'll stop here. Thank you for attention. I apologize for going over time.